Okay, welcome to a introduction to Petri nets in the context of simple neural models. And this is a fragment of a model for autoassociative memory. And it illustrates some Petri net concepts and two concepts from such a memory. So let's talk through the neural notions first, and then we'll talk about how the Petri net makes those work. We have a notion of a detonator synapse whose characteristic is that it's going to generate so much signal into the principal cell that the principal cell has a high probability of firing. And then we'll have another set of inputs that will propagate into synapses that are subject to Hebbian learning. And the Hebbian learning happens under the simultaneous condition of the synapse receiving a signal from the firing of the input cell and the depolarization of the downstream cell, the downstream principal cell. And as a consequence of that, then the weight associated with the synapse will increase. In this particular model, the weight is modeled as either 0 or 1, non-existent or fully existent. Okay, how does this work in the Petri net concepts? The labeled circles are places. The set of places in the Petri net and the presence or absence of the tokens, the black circles, defines the state of the Petri net. The places can be viewed as a vector whose values are 0 or some number of tokens in a given place, and that is the marking of the overall Petri net. That's its state. Okay. Between the places, the rectangles are transitions, which denote some process of moving from one state to another, and the way that flow goes is denoted by the directed arcs. So on the right hand side we have a detonator place that is marked, and it's the only place that has an inbound arrow into the transition to its left, T0, and therefore that means that that transition is enabled to fire. When it does fire, the outbound arrows tell us what places will be updated as a result. So the inbound place will fire. The 1 over the arc from detonator to T0 says that 1 token will be consumed. The outbound places will be populated with the number of tokens associated with them, either 1 in one case or 5 on the arc going to the principal cell. So what are we saying there? We're saying that this transition conceptually models two ideas. One is that a lot of signal will be propagated into the principal cell, and as a consequence of that, that cell will fire and will become depolarized. So we get both a lot of signal and we get depolarization as a consequence of that. So that's a single transition firing. Let's actually watch this happen. Let me zoom back out. When we shift over to execution mode in this Petri net editor that we're using, you'll notice that some transitions are colored red, and that indicates that they're available for firing. In this case, there are two transitions that are enabled for firing. Both of them have one inbound arc. Both of those arcs but both of the places are marked, and therefore each transition could fire. So let's watch one fire. All right, so in this case, the input place after firing is now empty, and its single outbound place, the synapse, is now marked. And if we fire again, we'll see the detonator place is now empty, and the principal cell has a large quantity, 5 being treated as large, of signal, if you will, and at the same time we have the depolarized place signifying that the principal cell did fire. So now we have the two events that are required for Hebbian learning. The synapse has signal from the upstream cell body, and the downstream cell, the principal cell, has depolarized. And so as a consequence, we have one more transition that's enabled for firing. We'll fire it, and the wait place now is now marked, and that wait will stay there, such that in the future the transition that goes from this synapse to the principal cell will be enabled for firing. If the synapse were marked and the wait is marked, then both of the inbound arcs into this transition are marked, and it could fire and propagate more signal. Okay, want to talk about the mapping between these Petri-net concepts and neural concepts. The notion of arcs linking transitions to places has a fairly natural interpretation as an excitatory process. So consuming a signal at one place and producing it in some outbound set of places has a pretty natural interpretation in neural terms. What we've seen in most of these places had 0 or 1 tokens, which maps easily to computer science notions of gates being on or off. The principal cell was an exception to that. It has 5 tokens, and mapping there, the obvious interpretation there is that more tokens represents more signal. Could represent a higher firing rate, could just represent a greater degree of depolarization, perhaps sufficient to cause the action potential to be generated. So I think there's one other important concept to point out here, and that is we saw that when we entered the simulation mode that 2 transitions were marked red, enabled to fire. The entire execution mechanism of Petri-nets is asynchronous and driven only by the availability of enabled transitions. There's no central point of control. If a transition is enabled, it will eventually fire, and in stochastic order. So that maps fairly well to neural processes where we have a bunch of concurrent things happening, and in general no central control mechanism. There is one caveat to that in the neural world, and it's important for this model, which is that there's a huge amount of coordination that happens through the oscillatory processes in neural systems, which are very timing dependent. So this particular little model here doesn't directly have a notion of time. There's a logical notion of concurrency that is captured by the notion of enabled transition. So we saw that when the synapse place and the depolarized place were both marked at the same time, quote unquote, this transition became enabled for firing. So that's kind of a logical notion of at the same time when two places are marked that are the inbound requirements for a transition. That's as close as we get to a timing concept right now. There is a more explicit notion of time that I'll talk about later, but for right now, that's what we've got. So I think I'm going to pause and we'll move to a different topic. Okay, we're going to walk through the third concept of this auto-associative network, which is integer division. And let's start with an arrangement of 2 by 2 weighted synapses. Let's suppose that previously, through the mechanism we've already seen, we had weights populated in 3 places the 2 inputs on the far left side, input 1 and input 2, were associated with weights 1, 2, and 2, 2, the right-hand column. So we had, if we imagine, one detonator synapse that was associated with both inputs, input 1 and input 2. Previous to that, we also had this weight 2, 1 populated, and we'll use that as an example of how the integer division works. We've got 3 weights here and 2 inputs. Let's step back and look at the rest of the components here. Coming down from these inputs, there's, over here on the left-hand side, there's long arcs that end in a circle rather than an arrowhead. Those are coming into the T6 transition. Those are different kind of primitive in the PetriNet world. They're inhibitory arcs. And what that means is when the place connected to an inhibitory arc is populated, then the transition will not fire, regardless of anything else about its state. So let's look at one in a little more detail down here. So let's look at this horizontal transition here where my cursor is. By the way, there's no significance to the distinction between horizontal and vertical or even angled transitions. It's just for this convenience of the layout of the PetriNet visually. All right, so this particular horizontal transition has 2 excitatory inputs from cell 1 on the inhibit 1 place, and 1 inhibitory input from activation level. What that means is if activation level has 1 or more tokens in it, then that transition won't fire regardless of the state of its other inbound places. So inhibition is an obvious correlate to neural concept of inhibition, but in PetriNets it works differently from the excitatory concept. The excitatory concept maps reasonably well to the notion of a graded response. More tokens will have more of an impact on the downstream places. But an inhibitory place is binary. If it's got no tokens, it has no impact on the transitions. If it has 1 or more tokens, it will completely inhibit the transition. So that doesn't map well to the graded response that inhibition has in neural systems. So what you'll see here is that inhibition gets used in 2 different ways. One is kind of just a simple flow of control, turning things on or off. And the other is in combination with additional logic, we can make it look like a graded inhibition concept, which is really what this integer division idea is all about. All right, so let's see this in actual execution. Okay, we have two enabled synapses. Sorry, two enabled transitions from the two input places. Let's let one fire. Okay, so the input 2 place emptied and the T23 transition fired, and it is meant to evoke a notion, for example, of an axon where we have multiple downstream synapses marked and potentially available for firing. In this particular case, in this second sort of input configuration, we have both weights 21 and 22 populated. So both transitions to their right are enabled for firing. And those are inputs down into the cells down below, cell 1 and cell 2. We can think of those as principal cells. And just as before, where we had a detonator that put a lot of marking into a principal cell, each of these transitions will deposit, in this case, one marking into that cell. And the question is will there be enough markings for the cell to fire and generate output? And that's where our integer division implementation comes in. Let's keep firing. Okay, so the other input place fired. It also propagated signal into both of its downstream synapses. But in this case, weight 1, isn't populated, the one on the left, and the one on the right is populated, weight 1, 2. So only one of the two transitions there is enabled for firing. Okay, so let's, one of them fires and it populates down here into cell 2. However, I want to talk about this activation level place for a minute, because this is the beginning of our integer division implementation. So we originally had places marked input 1 and input 2, and now the transition that they fed down to, T6, is now enabled for firing. And it's enabled for two reasons. One is that there's one or more tokens in activation level, which is its inbound excitatory arc, and there are no longer any tokens in the input 1 and input 2 places, either one of which would have had been inhibiting this transition from being enabled. So in this particular case, this is the use of an inhibitory transition for flow of control purposes. I didn't want this transition to fire until all of the inputs have propagated. So this is just a simple logic kind of gate mechanism. As we get further down into the bottom part of the picture, we'll see inhibitory arcs used as part of this sort of graded inhibition implementation. Okay, let's keep firing here. Okay, so one token was consumed from activation level, and it produced tokens in two inhibit places, one for each output cell complex down here. And let's do it again. Okay, so the second synapse up here fired, and now we have two tokens in the principal cell. The notion of this integer division neural concept is that we sort of gate which output cells can fire by ensuring that the amount of activation that goes to their input, the principal cell, is at least as high as the amount of activation that was originally present in the input. So we had two tokens in the inputs, and we're saying that we're not going to get any outputs unless we have at least two tokens in the outputs. For networks that are not overly saturated, where not all of the synapses have weights. This works pretty well as a way to only retrieve the patterns that were originally associated together. And the way we're implementing this is that this activation level accumulated the count of the number of inputs that were active, and it's going to be compared to the activation that came from the firing of the synapses, and will only let synapses that have at least as much activation level fire and produce output. That's the goal. Okay, so all of the activation level has now propagated, and notice that the activation level was having an inhibitory effect on this transition here, which is now enabled for firing. Now that all of the activation level has moved into the inhibitory places are ready to do their division process, and so for flow control purposes, we didn't want to let that happen until all of the activation had been propagated forward. Okay, let's see what happens next. All right. The way this transition works is it's going to take one from each of the inhibit places and the cell places and propagate it over to this threshold place. And it'll keep doing that as long as both input places are marked. So for illustrative purposes, we have this other synapse that fired, and this might illustrate a different pattern that might have previously been stored in the network. For example, two detonator synapses firing against one input 2. That might have been another pattern stored in this network. But that isn't the one we want to retrieve here. So we want to demonstrate that spurious synapses don't generate firing inappropriately. And so we'll see how that works. So down here what we have is, because only one synapse fired into this principal cell, it's only got a weight of 1 here, and it has two tokens that represent the overall activation level. So when we do our integer division, 1 divided by 2 rounds off to 0, so we should get 0 in the output. Over here, our integer division was 2 divided by 2 rounds off to 1, and we should get output. So that's the difference between those, and let's see whether it actually works that way. Okay, so what's happened here is that we had 2 and 1 here, and this transition fired, and 1 token was consumed from each place, and so we have 1 token in this threshold place. But notice that now this place is empty, and it's a necessary prerequisite for this transition to fire. So this transition won't fire anymore because this place is empty, and this place still has at least 1 token there. One of its outbound arcs is an inhibitory arc onto this final transition. And so what this means is, as long as this inhibitory place is populated at all, it will prevent this last transition from firing, and therefore we will get 0 in the output place. So this set of places won't update any further. There's no place for it further to go because this inhibition blocks this transition, and there's no more marking here to flow. So output 1 will be empty as required, and let's watch the rest of this. So this transition fired again, and we implemented sort of 2 divided by 2. Now both places are empty, and because this place is empty, it's no longer inhibiting this transition. The last thing I want to show is a particular kind of arc weight here. So the arc from threshold 2 into the divide 2 transition it doesn't have a number, it has an expression, pound threshold 2. And what that means is the number of tokens in threshold 2 will be consumed when this transition fires. The output arc, it's kind of hard to see, but the output arc just says 1. So the output from divide 2 into output 2 will just put 1 in, and the input will consume all of the inbound tokens. So basically what all this says is however many are in threshold 2 will get consumed, and we'll put exactly 1 in output 2, which is what we wanted to do. Okay, let's watch that fire. Okay, no more transitions are enabled for firing. Our input pattern of input 1 and input 2 produced the single output in output 2 as we expected. All right, so that's the basic mechanism of the auto-associative network for the hetero-associative case. And next we'll see how the whole thing works. Now we're looking at a full network of 4 by 4, if you will. On the right-hand side, I've labeled the input pattern, the granule, to suggest the granule cells in the dentate gyrus, whose synapses are detonator synapses that are going to generate a large marking. And then on the left-hand side, we have the inputs that we want to associate with the pattern in the granule cells. In this particular case, we've got a pattern of 0011 that's expressed in the granule cells, and we're going to associate a pattern to it of 1000. All right, let's kind of race through this. All right, we see some of the transitions firing. We see, for example, that this detonator synapse has populated a lot of signal into cell 3, and that all of the synapses in the quote-unquote column above it, or the dendritic tree above this cell, have been depolarized. Okay, and meanwhile the input 1 has fired, and its axon, if you will, has propagated an action potential down to its synapses along the row here. And so that combination in exactly one place here at the 1,3 node is enabled so that we can update the weight. Meanwhile down here, the second granule cell fired, and now our weight's been updated here. The second granule cell fires, and so we have 2 cells that have been updated. Meanwhile, our activation level is exactly 1. That was the total number of activation on the inputs. So only cells where at least 1 has been activated are going to fire on the outputs. And so now the activation level has propagated over to these inhibitory places, and only cells 3 and 4 have any inputs to match up with the inhibitory place to do the division. So we have, in this case, 5 divided by 1 is more than 1, and therefore this environment should fire. Whereas over here we have 0 divided by 1, and we shouldn't get any outputs. And it'll take us a minute to do that. And so all of our output places are populated, 3 and 4, and we notice that the weights up here, weights 1,3 and 1,4, have been updated such that in the future we should be able to retrieve this pattern. Okay, so that was the first phase, where our granule cells fire, imposing a pattern on the network, and now at some future time, let's assume that we get our associated pattern of 1000 that's presented on the left-hand side. We'd like to see whether the output that we expect is produced, that synapse over on the fire side will fire. It propagates down its axon. The two weighted synapses are now enabled for firing. They come down here. The activation level, meanwhile, has also been propagated, so only cells where at least one token has been populated will be eligible for firing, and this one is already eligible to fire. This one also is now eligible to fire, and we retrieve our output pattern, and the network has stopped executing. There's nothing else to execute. So that demonstrates heteroassociative retrieval. So that's a working set of PetriNet components to implement that neural concept. Okay, I think that was fun and useful to see PetriNet grind away transition at a time, but it's time to step back and look at the bigger picture. I have two questions I'm wrestling with. One is, are PetriNets a useful tool for modeling neural processes? And second, is it useful to model at this level of detail? So as a pedagogical tool, I think PetriNets have a lot to offer. They're visual, easily modified even by people who don't have any programming experience. As a formal tool, the formalism is simple enough that there are a lot of analysis techniques that can be brought to bear. We can figure out whether a particular state is reachable at all, whether a marking will grow infinitely, meaning whether it's unbounded. Safeness has to do with whether a place can have more than one token in it. So a lot of concepts that can be explored analytically, and that's probably feasible for small components like the 4x4 heteroassociative network I just demonstrated. At a larger scale, it's maybe doubtful that they'd be feasible. Bigger question is a nail and hammer question. I've been working with PetriNets for a while in anticipation of using them for this work. So that's the hammer I've been thinking about. Question is this the right nail? In particular, is it the right nail at this granular level of detail? The demonstration I just showed is a low-level model. When I originally started working with PetriNets, it was in the context of a much larger project at ICSI, the International Computer Sciences Institute outside of Berkeley, and the video I've got here demonstrates that project and the use of PetriNets at a much higher level of abstraction for the representation of actions in language. Looking at the problems of spatial navigation, I haven't been able to come up with a useful intermediate level of abstraction, so I'm working at this quite detailed level. So let's talk a little bit more about what that means. The one concept I haven't demonstrated yet is that of a timed transition. The transitions we've been looking at so far have been what are called immediate transitions. They take logically no time. There's no explicit concept of time in the PetriNet. We can introduce an explicit concept of time. So, for example, we might have a set of transitions, all of which could fire, but some of which might have a timing delay imposed on them of, say, 10 milliseconds. Others might have a timing delay of 50 milliseconds. And the PetriNet can run a virtual clock such that after 10 seconds has elapsed, all of the transitions that have a 10 millisecond delay will fire, quote-unquote, at once, regardless of how much wall clock time they take. We'll pretend as if they're all firing simultaneously at 10 milliseconds. And then 40 milliseconds later, all the transitions that are eligible to fire at 50 milliseconds can fire at once. And so using that mechanism, we can implement a lot of the timing-dependent behavior of neural processes. Obviously, that comes at a cost of additional complexity. I've been I spent a couple of weeks so far actually building Petri nets and modeling things. Currently, I'm working on modeling the head direction system. I have individual components of that system working. So, for example, the model I'm following supposes that we have head direction cells arranged in a sort of theoretical ring, and the head direction cells have strong excitatory connections locally and strong inhibitory connections remotely, which leads to some attractor dynamics. And then there are vestibular inputs that constitute self-motion information and visual cue inputs. So I have individual pieces of that working, but the overall system doesn't yet show the attractor dynamics that it's supposed to. And I think that is symptomatic of the sort of challenge that I'll have over and over again in trying to build up these detailed models. And at some level, that's maybe my strongest stock in trade. As a software guy, I've got a fair amount of experience with these kinds of problems. The first one is scaling up. The 4x4 network I demonstrated for the heteroassociative example is a good idea to get the concept across, but obviously isn't useful at that scale. So one of the things I added to the PetriNet pipe software was an ability to run PetriNets programmatically, to build them and run them programmatically so that we can scale them up as much as is necessary. Second thing I've done in the past for systems like these is I built a little framework for exploring parameter spaces. I assume that some of the behavior of a system like the head direction system is a direct result of the implicit parameters defined for it. For example, how active is active, how much marking, how many tokens constitute a maximum activation level. What's the relationship between the maximum excitatory level and the maximum inhibitory level? What's the ratio between the excitatory levels between the head direction cells and the excitation that comes from outside, that is from the self-motion cues and the visual cues? How many cells do we need? Petri nets are based on integer math, although it's possible to do real numbers in Petri nets. This particular version of the software doesn't include them. But if you get the numbers big enough, discrete integer-based behavior can begin to look increasingly like continuous behavior. So maybe it's just a question of scaling up the numbers. Those are the sort of parameters that I need to be able to explore systematically, and I do have some framework to do that. I'm a huge believer in automated testing. I put a lot of my effort into making sure that the software I work on has tests from the most granular level of code on up, because in my experience, you only get stable complex systems when the individual components are well tested. And I have a lot of general experience putting components together. I extended the PetriNet software quite a bit in order to enable PetriNets to include other PetriNets to an arbitrary level of complexity, and to include components in other software environments. So, for example, the YouTube video that referenced earlier shows an integration with Python. So those are the things I'm pretty good at, but modeling at this level of detail implies a lot of work, and before I commit to this path. I want to get some sense as to whether others think that this is a useful way to spend a lot of work. So I think that's rounds up my questions. Thank you for listening. I look forward to some thoughts.